This is the free response section of the June 2011 Chemistry Regents, and we're going to be going over the free response section, which is part B2 and part C, where we have these questions that require you add to the answer booklet that's designed for your test. So let's begin. 51. Explain in terms of protons and neutrons why uranium-235 and uranium-238 are different isotopes of uranium. Okay, the first thing here is that anytime you see an element dash with a number, you have to know that number is its mass number. And the reason is because that number signifies a different type of uranium. Okay, uranium is atomic number 92. Now, I don't need that number, but it tells me specifically that only uranium can have 92 protons. So if I write U, it signifies that, hey, I've got 92 protons in my atom, and only uranium can. But what can be different is the mass number. Why? Well, because protons, as you know, and neutrons make up the nucleus, and they make up the entire mass of the atom for the most part, with a slight amount of mass due to the electrons. So this mass number, okay, 235 or 238, tells me the exact type of uranium. Again, uranium, to be uranium, needs to have 92 protons, but it can have different number of neutrons. Okay, so 235 and uranium-238 are a pair of isotopes, same atom, different number of neutrons. And to get the neutrons, all you do is subtract your mass number from your proton number, called your atomic number. And that works because your top number is protons and neutrons, right? They have the same mass, and this number here is your proton number. Any case, they want you to explain in terms of protons and neutrons. You've got to be careful how they want you to answer these questions. All right. So in terms of protons and neutrons, why uranium-235 and 230 are different isotopes of uranium? Well, I kind of already have answered it, but very clearly, they're isotopes of uranium because they have the same number of protons but different number of neutrons, and that makes them a different type of nucleus, sometimes less or more stable. Okay, and these are both radioactive elements. Okay, they're beyond atomic number 83, so every isotope is radioactive, but this has 3 more neutrons. Okay, if you wanted to get that number, all you got to do is subtract 235 from 92, and again, 238 from 92. So, but all they're saying, hey, in terms of protons and neutrons, why these are different isotopes. Okay, so you've got to say protons and neutrons. And again, same proton number, different number of neutrons, right? The top number is protons and neutrons. The bottom number is protons. Okay, so let's go to the answer booklet. Okay, so I said U-235 and U-238 have the same number of protons. That's why they're both still uranium. Okay, what makes them uranium is a 92 protons, unique number, but a different number of neutrons. And that's why they have a different mass number. What makes up the mass of the atom is the neutrons and protons. If you go to table O, you'll see that the neutron has a mass of 1, no charge, and a proton, mass of 1 and a charge of 1. So they both have the same mass. That's why they contribute to this top number. But, okay, you could also answer this many different ways. You could say, hey, uranium-238 has 143, okay, neutrons. And uranium-230 has 146 neutrons, both having 92 protons. You could be more specific if you wanted to. And again, the way that I got the number of neutrons was I subtracted the mass number from the atomic number, okay, or the atomic number from the mass number, if I want to say that correctly. But I subtracted these two numbers because this is protons and neutrons, this is protons. So this is how you would get neutrons if you needed to. You didn't have to be this specific, okay. This would suffice, but there's many ways to answer this question. But be careful, you had to say something about the protons being the same and somehow talk about how this number was different in terms of neutrons. You had to mention neutrons and protons. That's how they asked you to answer the question. Number 52. Okay, number 52 states the bright line spectra for 3 elements and a mixture of elements are shown below. So they've given me the bright line spectra. Now this is hard to do in black and white, but what this should be is actually bands of different colors representing the different wavelengths of energy that are emitted when elements get excited. So if you did this in class, I know that we did shot these gas discharge tubes. We used a diffracting lens, and you were able to break up the light into its individual wavelengths or frequencies, and you saw the different colors, and every element has a unique spectral footprint that describes themselves in terms of their energies, which are associated with the movements of electrons. Every element has a unique energy arrangement with its electrons to its nucleus. So in any case, you have these three elements, lithium, cadmium, and then you have a mixture. And number 52 states, explain in terms of both electrons. Again, they're being explicit how they want you to explain things. In terms of both electrons and energy, how bright line spectrum of an element is produced. So you should know, we'll use shells of electrons. Okay, here's our nucleus, it's positive. And here's some shells that talk about proximity to the nucleus. Now we know electrons do not go in circular orbits, that's the Bohr model, but we'll use that analogy, okay? So if I have electrons that are closer to the nucleus, and I have electrons farther to the nucleus. Okay, well electrons that are closer to the nucleus, that are filling in lower energy levels first, okay, are said to be ground state and stable. Okay, if they're stable, they have low energy. Now if they have low energy, and the reason they have low energy is because they are really being attracted by that positive nucleus full of protons. Now, if I was to give this electron some energy, like a flame from a candle or a burner, okay, if I gave it some energy, now this electron has enough energy to overcome this electrostatic force, or the positive pulling force, right? Positives and negatives attract. Electrons are negative. So if I give this electron enough energy, it can overcome this attraction and get to another energy level. But that energy level is specific. We have to have an exact amount of energy to get there. It's called quanta. Okay, we say the atom is quantized. It's a quantum leap. So if you don't have enough energy, you don't get there. It's all or none. If you have it just enough to get to this level, you would. But let's pretend that this energy that was accepted by this electron made it leap to this energy level farther away. Now, this electron, okay, is said to be now unstable and excited. Remember excited state configurations that are leaving a place where electrons should be? Well, now it's unstable with high energy, okay? And this unstable high energy electron won't exist in this situation very long. Things with high energy tend to do something. So what this electron will do, it will leap back eventually to its ground state. And when it leaps back, it has, with its high energy, it gives off, okay, or emits, okay, light in the form of electromagnetic radiation, or photons is the word you can hear here, or spectra, okay, as it gives off its energy as it jumps back. So in terms of electrons and energy, that's how it works. So let's put that to words in the answer booklet. Okay, so I said excited electrons that are high in energy release or emit energy in specific amounts as they return to their low energy stable ground states, and that would earn you a point. The other one I had up here, I think I got right, is also a point. Now you certainly could say this in many different ways. You could say that, you know, electrons that are farther away from the nucleus have to give off that extra energy they had to get there, and that energy given off was exactly equal to some specific amount that's unique to every atom, because every atom's a different number of protons and therefore different attractive forces and different number of electrons. There's many ways you could say this, but that would suffice. You can say this easy. Energy is emitted when electrons fall back to lower energy shells. So many ways to say this, but you had to talk about electrons, okay, and you had to talk about energy. Okay, and you should know electrons existing farther away that are excited, okay, have higher energy because they can overcome that positive pulling force of the nucleus. Electrons that exist closer have lower energy because they can't overcome that. That's why they exist closer. Okay, so that is the basic answer for number 52. Number 53. Number 53, identify all the elements in the mixture. Okay, so if we're going to go to the mixture, we need to see our spectral data. And there's our spectral data. So this is a mixture of elements from these three. So I'm just matching up the spectral lines. So strontium give these unique spectral lines. You can see that these lines are the same, okay, matching in the ones below. So we definitely have strontium. We do not have any cadmium because, as you can see, if there was cadmium, we would have some lines here. These two lines would be shown here and here. So cadmium is not here. And do we have lithium? It certainly looks like we have lithium. This line came from lithium. Okay, and looks like this line is associated with lithium. And looks like this line could come from lithium as well. So it looks to me like we are sharing some lines here. So certainly this tells a story here. This cadmium we don't have. So this line definitely came from lithium. So you definitely have lithium and strontium. These spectral lines, when you put them on top of each other, would give this associated pattern. Okay? And again, all I'm doing is matching the lines. Okay? All right, so number 53, okay, is we have our strontium and our lithium. So let's put that down in our answer booklet, number 53. So number 53 is strontium and lithium. Number 54. In number 54, typical question where we have all this information and they kind of give you some concept question based on what you were looking at. So this is state the total number of valence electrons in a cadmium atom in the ground state. So let's go find cadmium in the reference table, and that will give us a clue about its electron configuration. Let's go there. So here I am with the periodic table, and I see that cadmium, okay, is under zinc, and cadmium is one of those metals that have electrons that are, well, now filled in that D subshell, but it's part of these middle transitional elements. Now typically zinc and cadmium and mercury are not considered to be transitional elements, but they're not going to get to those very, very big details here. All they want to know is valence electrons, and these electrons are available for bonding. And metals tend to lose, in fact they definitely lose electrons because they become positive. You can't find a metal that becomes negative. So the electrons available for bonding for cadmium, like zinc and mercury, depend on which electrons or how many electrons it loses. For instance, aluminum, like boron, likes to lose 3. Now it's kind of clear that 3 electrons is the last number. Now cadmium, okay, even though it's got a more complex configuration, that last number there are those electrons available for bonding. The proof is that cadmium becomes +2, just like zinc. Zinc has 2 valence electrons that it loves to lose. Where they come from, not part of this course. But cadmium in the same column, notice, has the same type of valence electrons. So we're going to say that zinc, cadmium have 2 valence electrons because they can lose 2 electrons to bond, to become +2, or that last number is 2. Okay, and again, this becomes more complex as we go to the other transitional elements, because you could say, well, nickel, that loses 2 too. But how does it become +3? Well, it can lose 2 or 3. So nickel could have 2 or 3 valence electrons. But they're not getting that advanced. They just want you to realize that, hey, what is the outermost number of electrons that it can lose? Okay, so that's that number there. Just like, hey, if you went over to nitrogen, what's the valence electron? 5, okay? So that number is just 2 for cadmium. So you would just say 2, okay, and that gives you a point. Number 55. So number 55 is the graphing question, where they want you to plot this data, which is the atomic number to the ionic radius, kind of like what we did with our periodic table graphs we made for a lab. And number 56, on the same grid, plot the data. So they want you to make an appropriate scale, okay, and then of course they want you to plot the data. So I'm going to go ahead and do that on my graph, and I'll get back to you in a second. So number 55, they want an appropriate scale, and the values I'm using is the ionic radius going from 44 to 134. So when I go to my scale, I want to extend from the 0 to at least 134. So 0 to 140 was my stretch, or my legend there. And let me just go there to show you. Okay, and there it is, 140 I used all the way up and to the 0. And you could have figured that out because there's 1, 2, 3, okay, 4. There's 1, 2, 3, 4, 5, 6, 7, 7 big boxes. And if you're trying to go to 140, then I made every big box equal 20. I mean, there's many ways you could have done this, and if you didn't use the entire graph, that's okay, but you don't want to have is breaks. Yeah, we don't want any breaks. Do not do any breaks. We want a continuous linear scale where this scale stays even. So if you're gonna make this 20, it should stay 20 throughout, and that gives you a point. So no breaks, and you kept a continuous scale, okay, so that we can see a trend. Now, it's important, if you didn't use the entire graph, if you were to stretch this down into a very tiny little point here, made every one of these 10, 20 small, and we couldn't see the trend because your scale was so small and you didn't use the entire graph, you would lose the point. So you didn't have to use the entire graph, okay, but it had to be a continuous pattern of 20. Whatever your key was going to be, your legend, you got to keep that the same. So 20 points between these big boxes, you got to keep that, okay, no breaks, continuous, and if it's large enough to see a trend, okay, and that would give you, okay, the 1 point for 55. Now 56 asks you to plot the data. I'm going to do so now. Number 56 asks you to plot the data from the test onto this grid, okay, and they asked you to circle your plots, your points, and connect the dots, okay. To get a point, you have to make sure that your plot or your point is plus or minus 0.3 of the grid space. So make sure that you do a careful job of placing these points. Do not get sloppy and rush through this. You'll miss a nice easy point. So go through your data, make sure you put your point exactly where it belongs based on, you know, your scale, obviously. Now if your scale is corrupted and bad, I think there's no double jeopardy. Based on your scale, you'd get this point, but make sure you plot them correctly. Don't get lazy here. And you're going to get a point if you plot them carefully and within that plus or minus 0.3. Okay, and someone is going to take this test and look at these points carefully based on your scale. So don't get lazy here. All right. Interesting enough, if you didn't circle or connect the dots, even though they asked you to, you'd still get that point there. Okay, so number 56 is just plotting the graph as shown here, something that we should be able to do from 6th grade or 4th grade on. Any case, number 57 is next. Number 57, estimate the ionic radius of strontium. Now, like many of these graph type questions, after you plot the graph, there's going to be at least one question on the graph. So they want to estimate the ionic radius of strontium. Now, strontium is not listed here, but from the graphical relationship that we made, we should be able to read on your line that you made, okay, what strontium is once we know its atomic number. So let's go find the atomic number of strontium and where it fits on the graph that you made in the answer booklet. So strontium, if you did not know, is an alkaline earth metal, group 2, and its atomic number is 38, and we'll need that to go to the graph now that we just made. Number 38 for strontium. Okay, so 38 is our number here. We have 2, 4, 6, 8. So remember, this would be 32, right? These dots, this is 32, 34, right? This is 36, and this would be 38. So right here is the 38 line. So we're going to follow this line all the way up Strontium is atomic number 38. I'm going to use the relationship. Okay, this is where the line definitely helps, and I get a point right on that line. Now you're going to get some leeway here, but my point that I get, okay, gets me to this position here. Okay, so between these two boxes, I have 120 of 20 points. So 1, 2, 3, 4, 5. So if I've got 20 points, okay, I can split that up. So knowing I have 20 points in between, and there's 1, 2, 3, 4, 1, 2, 3, 4, and 5 positions. So take the 20, divide by the 5, and you get 4. So this would be the 104, 108, 112, and of course 116. Okay, so what you would get is 116 based on my graph. So 116, okay, picometers is what I would get, and they give you plus or minus 2 here. Now I got 116 from reading my graph. The answer supposedly is 117 plus or minus 2. So I have the range of anywhere from 115, okay, to 119. Okay, I got 116, and that falls in that range, and that gives you a point. So you can see if you're not careful in that instance, reading off the graph, very easy to get this wrong. So be very careful. A lot of times the questions are, state the trend? Is it going up or going down? This one actually quantitatively wanted a number. Okay, number 57 is 116 or 117 officially, plus or minus 2. Number 58. And number 58 is that question I was talking about. State the trend in ionic radius as the elements in group 2 are considered in order of increasing atomic number. Okay, you probably don't need the graph because as you go down any column, the radius gets bigger. That's why we become more metallic. Electrons are easily lost because they're farther away from the positive nucleus. But if you need the graph, okay, we'll go there. And from the graph, and you should look anyway because sometimes things aren't as obvious, but in any case, this is clearly going up as the ionic radius increases, as the atomic number increases. Okay, that's the basic trend here. So number 58, as the atomic number increases, the atomic radius increases. Okay, so very simple, and you could say this in many different ways. You could basically say the ionic radius increases, okay? Or in group 2, as you go down a group, it increases. There are many ways to say that. Bottom line is, as the atomic number increases, so does the atomic radius. And we know that's because of that shielding effect, or adding electrons to rings farther, or shells, I should say, not rings, shells farther away. Okay, number 59. Okay, number 59, explain in terms of electrons. They're asking you to explain in a certain way in terms of electrons, okay, why the ionic radius in group 2 element, okay, is smaller than its atomic radius. An ionic radius, that means when it becomes an ion. And its atomic radius is when it's the size, when it's still an atom. Well, group 2 elements all become plus 2. Calcium atom becomes calcium plus 2. They all have 2 valence electrons. There are the alkaline earth right here, plus 2, calcium plus 2, strontium plus 2. They all have, there it is, that outermost 2 electrons called valence electrons. They like to lose them, become as stable as a noble gas electron configuration. So they all become positive. Like all metals become positive. You can't find a metal that doesn't become positive because metals are big atoms, they lose electrons. So this is the atom when it has the equal number of protons and electrons. It's electrically neutral. Here is the ion when it becomes charged by losing 2 electrons. If you want to write the oxidation half reaction, it looked like this. Okay, but there's the ion. Now where they're saying why the ionic radius is smaller, that means the atom, okay, is large. When it becomes an ion, it gets smaller. So why does it get smaller? Okay, well, in terms of electrons, this has 2 less electrons. And if you think with me for a second, if it has 2 less electrons, now the protons outnumber the electrons. When it's an atom, we have the same number of protons as electrons. This is atomic number 20. This is 20 protons and 20 electrons. Here it's still calcium, so it's still atomic number 20, or 20 protons, but it lost 2 electrons. Now it has 18 electrons. So the protons outnumber the electrons, and if they do that, the protons will now pull in and attract the electrons more, making the radius smaller. Now you can also say that calcium lost 2 electrons in its outermost shell. So now it has electrons in a shell that's closer. Okay, so many ways to say this. Now calcium has a configuration of 2-8-8-2. And calcium plus 2 is 2-8-8. So you can see that the outermost electrons in the 4th energy level were lost. So you're left with electrons that are closer to the nucleus. So many ways to speak on this. Let's go to the answer booklet. So I said the metal ion has 2 fewer electrons, thus the protons attract the remaining electrons more. Many ways to say this. You could say that the group 2 ion lost its valence shell, its outermost shell, so the remaining electrons are now tucked in closer in the kernel part of the electron configuration. So many ways to say this, and that would get you your point. Number 60. Number 60, determine the oxidation number of chlorine in the reactant in the equation. Okay, so my reactant side is clearly going to be this side. That has to be clear. Reactants react to make products. So this is the reactant side. Let's zoom in a little bit. So they want the oxidation state, and this was the first skill in Redox. So let's get this a little bigger. Okay, and this is how I do things. Maybe your teacher taught you a little differently, but what I'm going to use is the overall charge of the compound to get the individual charges. Now here's what I'm going to do. I'm going to get rid of, this 2 here. This 2 does not help me. It doesn't change anything. It confuses people. I'm looking for the individual oxidation state. So when I'm trying to determine the oxidation of chlorine, I want the individual charges. What I'm going to use is the overall charge of the compound, which I know to be 0 because this is not a polyatomic ion. I don't see any charges. I got rid of the 2 in front just so that you can clearly see it has nothing to do with the individual charges. Okay, so now when you have 3 of these compounds, 2 of these oxidation numbers you have to know to get the third. Or after the chlorine. Let's go to the periodic table and look up K, oxygen, chlorine, and let you get some hints here of how we should start this. First, you should already know that a group 1 ion like potassium, alkali metal, only has one choice, +1. So we're going to definitely start there. And oxygen, 99% of the time it's -2. They don't put the other ones there. They want you to use a -2. The chlorine is our problem because it has multiple oxidation states. Problem here. We can't start with the chlorine. If it'd be nice, it'd be done. So we're going to use the 2 definites, the oxygen that's -2 and the potassium that's +1 to get that. So armed with this information, we have oxygen that's -2. We have potassium that's +1 individually. Now, each oxygen is -2. There's 3 of them. 3 times -2 is -6. Each potassium is +1. There's only one of them, so it's +1 individually. What number plus a +1 and a -6 gives me 0? And you can think, whoa, that has to be a +5. And because there's only one chlorine, that number is +5 for the chlorine. It's as simple as that. So number 60, write +5. 5 would be acceptable, and of course that'd get your point. Number 61. State why the entropy of the reactant, that's a solid, is less than the entropy of the products. Well, a solid has a regular repeating crystalline structure. okay, that repeats in all directions and is very ordered. Entropy is the measure of disorder or chaos. And we know that solids are more ordered than gases. Now we're making two solids here, but we know that we have one particle breaking apart into two, actually 5 particles. These are solids, but 3 gases. So one particle breaking apart into 5 particles, 3 of which are gases, means that the entropy is so much greater for the products because of the gases, which have much more disorder because they have so much energy and so much randomness compared to the solid, crystalline, ordered structure of the reactant. Number 61, let's go to the booklet. So I said the products contain 3 gas molecules which are more random and disordered than the solid. Okay, and that gets you a point. Many ways to say that, many things you could have said to show that there is more disorder in the product side than the solid reactant. Number 62. Number 62 has a little paragraph here, a little blurb, and it has, with this little blurb, some information in terms of a graph. And I know some people get intimidated by all this information, a lot of which sometimes are not even asked for in the problem. So some teachers, including myself, and again, follow your teacher's advice, I tend to look at the question first and go back. But let's just look at the information given because it's not so eclectic, it's not so foreign to us. We have a container at a certain temperature, and we have a certain amount of CO2 and a certain amount of H2 in a 1 liter container. So we've got gases that are in a container. Okay? The substances react to form new gases. Okay? So the container is basically a big, let's say a big box, and you're starting out with CO2 and you start with hydrogen. Over time, they're going to react together to produce some new gases, CO, carbon monoxide, and water vapor. So that makes sense that over time our reactants are going to go to products, and our reactants should get lowered as they react, and as we make more and more products they should go up. Okay, and that's essentially what's happening. And if you look at the graph, we have our reactants, okay, and we have our products. And when we start at time 0, when there is no time before you started the reaction, we had 0 products and we had a lot of reactants. Now, as we just said, using just common sense, over time the reactants are going to react to produce products, so the reactants go down and the products go up, and they seem to level off here. And that's all that's going on here. Now, you certainly don't have to go through all of that to get to the questions, but I'm showing you that this isn't all that foreign. It looks very, very weird, but it's very straightforward. Let's go to the question. Again, if you didn't want to go through that, read the question first. Number 62. Determine the change in concentration of CO2 between time t0 and t1. So we go to the graph, and we see between, okay, time t0 is here, and time t1 is here. So we're looking for this time period between this and this. And they're talking about the change in concentration of CO2. Now, CO2, all right, is a, CO2 is a reactant, and we start with 1. Okay, we can assume it's right on the 1 because they say it starts at 1 molar. And it goes to time, okay, T1 here, which is this point. So from this point, how did the concentration change? Well, here's a concentration in moles per liter, which is a molarity, right? Molarity is equal to moles over liter. And they're giving you the concentration on the y-axis. And at time 0, we're 1.0. And at time t1, we're at, they're telling us this dotted line is 0.73. And what do they want? Determine the change from those 2 points. So they want the difference. They just want the difference. So all you're doing is subtracting those 2 numbers. So 1.0 minus 0.23 is 0.27. And again, these are molarities, so you subtract and you get 0.27 molarity. And that's all they wanted. Now, of course, I did a lot more thinking through this, but from this point to this point, 1 to 7.3, the difference between, looks like I'm drawing a face there, the difference between these 2 points is 0.27. That's all they wanted. Okay, so let's go to the answer booklet. So by subtracting those two numbers, I get 0.27 mole per liters, which is the same thing as molarity. They gave you the units, not looking for significant figures. They didn't ask for them, and that would earn you a point right there. Number 63. Number 63 asks, what can be concluded from the graph about the concentrations of the reactants and the concentrations of the products between time 1 and time 2? So, see, time 1 and time 2. So between these 2 points, what can be concluded? Let's change some color here. All right, let's go from this point to this point. So from these 2 points, what can be concluded? Well, at this time period, we have a leveling out of the concentration of the products and a leveling out of the concentration of reactants. They're staying constant. And if they are constant, that must mean the rate of the forward reaction is now equal to the rate of the reverse. You guessed it, we've achieved equilibrium. Remember the tank demonstration we did, or your teacher may have done. Equilibrium was not reached when the levels were equal. They were reached when the levels stop changing and you add the same amount of water going into one as you go into the other. So equilibrium. Let's go to, so again, I'm sorry, so back to the tank demonstration. The tank demonstration showed you that equilibrium was reached when these levels stayed constant. They didn't change anymore because we were pouring the same amount of water from one into the other. So let's go to the answer booklet. So I said the concentrations are constant for the reactants and products because they reached equilibrium. In fact, the scoring guidelines for the New York State Regents for this test did not include equilibrium. Although, to me, if you're reaching a conclusion, you should have that there. However, they just said, if you just said something along the lines that the concentrations of the reactants and products stayed the same, anything along those lines was acceptable. You did not have to include equilibrium. And I would think that that would be a conclusion. Okay, an observation is they stayed constant based on the line, but that's what they're accepting. So number 63, as long as you said something along the lines that these things are staying constant, not changing, okay, you'd get their point. Not necessary to have equilibrium, although I think you should, but again, I would stick to the scoring guidelines of New York State. Number 64. Number 64 states, identify the type of organic reaction that's given. So let's go read about this reaction. A reaction between bromine and a hydrocarbon is represented by the balanced equation below. Identify the type of organic reaction. Well, a couple of different things you could say. First and foremost, I can see that, wow, standalone element. That would scream to me a redox reaction. So you could say redox. Now, I'm not sure if they would accept redox here because they want the organic reaction. So it screams to me redox, but I'm going to try to answer this question by the organic, okay, naming. Now we should know that how did bromine, okay, attach itself to the carbon chain? You notice everything attached. Okay, this bromide opened up this double bond. And when it opens up this double bond, when it attacked the pi bond, it created one extra bond here and here. When you open up this double bond, each carbon is going to have one additional position to hold on to something new. In this case, it'll be two bromides. Now, I drew mine both opposite going up and down, but you can draw it any different way if you had to draw it. The bottom line is two bromides attach themselves to two different carbons that were spanning opposite sides of a double bond. And when you open the double bond up, both of these carbons involved in the double bond have, guess what, more opportunities to bond. With the double bond, you should know that this is something called unsaturated. Why is it unsaturated? It could hold more H's if this bond wasn't there. Carbon makes 4 bonds. So if it makes a double bond, it cannot bond to more things. This is now saturated because now carbon is bonding to the maximum amount of elements that it can, because every bond between the carbon is single bond. Now, we name this to be something called the addition reaction. And the reason why this is an addition reaction is because both bromides are adding to the carbon chain. Okay, two different carbons because they span the double bond. And everything adds to the chain because there is room once this double bond opens up. So anytime we're opening up double or triple bonds, we can add everything to the chain. If this was a saturated hydrocarbon, if we pretended for a moment, instead of propene, one propene, this is propane. So if I had propane instead, I'm not going to draw all the H's, I'll just use dashes, and I had bromide trying to attach to this, well, because this is already filled and already saturated with H's, an H would have to come off for Br to come on, and that we call substitution if this was an alkane. This, of course, is an alkene, and therefore it undergoes addition because there is room once you open up the double bond. Any case, this is an example of addition reaction. Okay? You could also call it halogenation or bromination. These are some weirder names. Halogenation we talked about in terms of adding halogens. That's the group 17 elements to the chain. Any case, the best answer, okay, is going to be an addition reaction. Number 64. Let's go to the answer booklet. I can talk. So there it is, an addition reaction. Again, you could have written halogenation. That's adding halogens to it. Okay, but addition is something you should be very aware of. It's a very common question. That gives you our point. Number 65. Write the name of the homologous series, okay, to which the hydrocarbon belongs. I know some people say, well, which one's the hydrocarbon? My friends in chemistry, hydrocarbons, they have hydrogen and carbon only. So, of course, that's the hydrocarbon. Notice the reaction. Look at the little blurb. A reaction between bromine and a hydrocarbon. That's the two reactants. So this is your hydrocarbon, something that you should know and understand and be able to identify a hydrocarbon, just carbons and hydrogens. Now, homologous series is how the carbon bonds to itself. We have three basic series. We have alkanes, alkenes, and alkynes, and it's based upon the bonds between the carbons. Let's go to table Q that outlines these three different types of family of hydrocarbons. So here's table Q, and look at the three different, okay, homologous series. It even says it right there. And what do we have? Alkanes have the single bonds between the carbons. Alkenes have the double, and alkanes have the triple. You should know that these ones, the top ones right here, are your saturated. They're holding the maximum amount of H's. Notice that H2N plus 2. And this is 2N and 2N minus 2. These guys don't hold on to the same amount of H's because carbon must make 4 bonds. So because there's a double bond in that halogen, the homologous series is an alkene. So number 65 is an alkene. Right from table Q, and there's our point. Okay, number 66. Okay, we got a little blurb here. Ozone's produced from oxygen by electrical discharge during thunderstorms. The unbalanced equation is below, so oxygen with electricity makes O3. Okay, number 66. Now, again, if you didn't like all that information and that was something that just really turned you off in terms of understanding what was going on, just go to the question. Balance the equation. You don't need to understand what's going on here to balance the equation in your answer booklet. Okay, so let's go there, number 66. So here is our reaction that it's not balanced. Law of conservation of mass states that we should have the same number of each element on both sides. I have 2 oxygen atoms here, and I have 3 oxygen atoms here. That is not balanced because we're breaking the law of the conservation of mass. We're creating an atom as we go across. So I have 2 oxygen atoms on this side. I have 3. I have to have the same number. So I need a common factor between 3 and 2, and that of course is 6. So I need 6 oxygens on this side. How do I get 6? Well, times this by 3. How do I get 6 oxygens on this side? Times this by 2. Notice the coefficient times the subscript will give us 6 oxygens on this side, and 2 times 3 give us 6 oxygens on this side. And now we are balanced. Notice the charge is the same. There's a 0 on this side, 0 on this side, and if we had energy, energy is also conserved. Okay, number 67. Number 67, identify the type of bonding between the atoms in an oxygen molecule. Okay, well, in our oxygen molecule, if we draw the Lewis structure, we have oxygen with 6 valence electrons, 1, 2, 3, 4, 5, 6. Another oxygen has 1, 2, 3, 4, 5, 6. And this really works well because when I do the Lewis dot diagram, this oxygen now is sharing 8, and this one is sharing 8. Okay, so they both feel like a noble gas in terms of electron configurations because of the sharing 2 from each other, and that's a double bond, 2 pairs. But what are we getting at here? Well, I'm getting at is the idea that these electrons being shared in a covalent bond, now covalent bonding is sharing, they're sharing equally. Very important you understand that. Why are they equally? Because they have the same electronegativity. So if we're saying the electronegativity here is 3.4 for oxygen and 3.4 for this oxygen, then, okay, they have the same strength or attraction. So the electrons are shared right down the middle, which means no one side of the bond feels more negatives than another. That's important. Okay, so all of our Hofbrinkels, H, O, F, B, R, I, N, Cl, apostrophe S, all of these elements, they love to bond with themselves. Okay, these diatomic elements, we call them Hofbrinkels, other people call them Brinkelhofs, or look at us funny when we say that. These are the diatomic elements that bond with themselves. All of these guys exhibit non-polar covalent bonding. Why is it non-polar? Because their electrons are shared equally, because when you bond with yourself, okay, or bond with the same 2 atoms, you have the same electronegativity between them, which means you're going to share those electrons equally. No one side feels negative. When we have a polar bond, for instance, HF, fluorine is much more electronegative. Fluorine has 1, 2, 3, 4, 5, 6, 7 electrons, and it takes 1 from the hydrogen. Okay, this pair of electrons, now I really should draw like this. 1, let me do, that's a good one, Grodsky. 1, 2, 3, 4, 5, 6, 7. This red one, okay, is being shared, believe it or not, okay, by the hydrogen. And we would say that this type of sharing is very unequal. They're more closer to the fluorine side. So the fluorine side is a little more negative than the H side. The H side is a little positive because it has electrons kind of pulled away. Now, why are these guys sharing unequally? Because they're 2 different atoms. And therefore, they create something called a polar covalent bond. There's poles. There's different. Okay, polar covalent bond. Nothing to do with the molecule yet. Polar covalent bond. And they're sharing unequally. Okay, so a little mini lesson there. So in any case, the bonding is clearly going to be non-polar covalent. So there it is, non-polar covalent. Now they would accept double bond. If you recognize that in my Lewis dot diagram, if you drew a Lewis dot diagram like I did and recognize that each oxygen is going to need another pair with itself, and you noticed it was a double bond, they would accept that wholeheartedly. Okay, so 67, non-polar covalent. If you said, you don't have to say covalent either. So non-polar, non-polar covalent, double bond are all acceptable answers. Number 68. 68. Explain in terms of electron configuration Why oxygen molecule is more stable than an oxygen atom? Okay, well, I kind of drew this up here already. All right, let's go with orange. All right, now an oxygen atom is electron configuration 2, okay, dash 6. Now, it needs 2 more electrons to be like neon, which is 2 dash 8. 2 more electrons. So when it shares a pair of electrons with another oxygen, it feels like it kind of gained 2 electrons to fill that octet, or that 8. Okay, when we fill and have that 8 on the outermost, it's very stable. Let's go to the periodic table for a second. This octet rule that we follow with ionic bonding and even covalent bonding is the idea that elements want to become stable. One of the ways to become stable is have a configuration or an arrangement of electrons that is like these noble gases. These noble gases are unreactive for the most part because they are low energy, which means you have to add a lot of energy to them to make them change. And what's special about them is they fill the octet, with the exception of helium, because it only has 2 electrons in the first energy level. So let's take a closer look. So elements want to become as stable as neon. So if you look at fluorine, and just again, fluorine likes to become -1. It's 2-7. So it likes to make or share 1 more electron with somebody to feel like it's 2-8. Notice oxygen becomes -2 by sharing 2 more. Notice nitrogen is -3, so you get the idea. Fluorine makes 1 bond. Oxygen makes 2 bonds. Nitrogen makes 1, 2, 3 bonds. Carbon from organic chemistry makes 1, 2, 3, 4 bonds. Why? We want to fill that octet. Okay? So oxygen is more stable bonded, and by bonded with oxygen, both oxygens feel like they have the configuration of a noble gas. Fluorine is more stable with itself because when it bonds to itself in a single bond, only needs 1 more electron, right? It feels like neon. And nitrogen, when it bonds to itself, is triple bonded because it needs 3 more electrons, okay, from itself. Any case, let's go to the answer booklet. So I said both oxygen atoms have achieved a noble gas configuration. I mean, many ways you can answer this. They both satisfy the octet rule. They both have 8 now. Okay, and certainly there's other things I'm sure you could say that are equally correct, but that is sufficient, or something along those lines, to earn your point. Number 69. Number 69 has another blurb here. Okay, and we have some natural gas components. Notice these are all organic compounds. The anes are single bonded, and the F is a 2 carbon from table P, 1 carbon. Any case, we have the boiling points. Again, if you don't like any of this information, if it makes you go a little crazy, cross-eyed, go to number 69. Go right to the question. Identify a process used to separate the components of natural gas. So natural gas clearly have, all right, different boiling points. And how could we separate something with different boiling points? Okay, these are hydrocarbons. These are fossil fuels. And I guess the best way to separate something based on boiling them at different temperatures is distillation. We did distillation of Coke, and we basically took a container of Coke, which is a mixture of, well, the Coke ingredients and water in a mixture retains individual properties, so it eventually, at a higher temperature, it boiled and separated off. It hit into a condenser tube where it was cooled and became a liquid, and we separated the water from the Coke. No big deal. Okay, but we did so because the components of this mixture had different boiling points. And because they were a mixture, they retain their individual properties. So if I've got a mixture of these guys, they're not chemically bonded, they can be boiled off at different temperatures, and distillation is how we would do that. Okay, now I'm not sure what other separatory techniques would be accepted, but let's go to the answer booklet. So distillation is really the best answer here. The booklet's going to accept, or the New York State accepts fractional distillation, and that's just a type of distillation where we use a column at different heights as the vapor cools from boiling it from below. So the vapor is boiled and it cools at different heights and collects and condenses. And fractional distillation is how we separate all the different components that we get from crude oil into gasoline, kerosene, diesel fuel, and so forth. But distillation is good nonetheless. Number 70. List the 4 components of natural gas in order of increasing strength. So we're going to start from the weakest strength to the strongest, and the key word here is intermolecular attractions or forces. These are not bonds, these are how molecules, and these are molecular compounds, they're organic. So all of these are organic or molecular, they make molecules. These are how they attract themselves. How does one butane molecule attract another butane molecule? Well, look at the boiling points. That's the key. If something boils at a low temperature, look at methane. Methane has the lowest boiling point. That means it takes the least amount of energy to separate the methane molecules. These guys don't attract each other very well. That's why it doesn't take much energy to boil them. So we would say that methane had to have the weakest attractions because it has the lowest boiling point. Think if you had liquid nitrogen in your class. That liquid boiled so rapidly at room temperature. Why? Because its attractive forces are very weak. Water doesn't boil at room temperature because its attractive forces are strong. The liquid molecules are holding on. So you see that the lower the boiling point, the weaker the traction. And the higher the boiling point, the more the compound resists breaking apart from each other and boiling and evaporating because they're holding on strong. So as my boiling point increases, ethane is next, okay, my intermolecular attractions, oops, didn't read it carefully, the propane is next, right? No, I was right the first time. So negative 161, negative 1, I'm coming up. So ethane, trust in yourself, okay? And then propane is next. And then of course, the one with the highest boiling point is the one that resists evaporation the most, and that's butane. So methane, ethane, propane. And look at this, party people. This goes in order of how many carbons you have. This is a 1-carbon chain. This is a 2-carbon chain. This is a 3-carbon chain. This is a 4-carbon chain. You learn this in organic chemistry. Larger the carbon chain, the stronger, okay, the weak forces or the London dispersion forces because of a greater amount of electrons in your cloud. But in any case, you don't need to know all of that. The bottom line is you can get that from the boiling points. So let's go to the booklet. So it's methane, ethane, propane, and butane. Just be very careful. They want it in increasing strength from the weakest to the strongest. So many people, when I grade this test, will get this reversed. You've got to really pay attention to what you're doing. One more point about this, butane is a 4-carbon chain. You guys know octane is an 8-carbon chain, right? There's my 8, C8. So octane, you guys know octane is in gasoline, and that's a liquid. These are all gases. How did a gas eventually become a liquid? Well, because the intermolecular forces increase as you add more carbons. Number 71. Okay, we're talking about the Solvay process, and here's the reaction. Don't want to confuse yourself. Go to the problem. Write the chemical formula for one compound in the equation that contains both ionic and covalent bonds. When I hear both ionic and covalent, I think of polyatomic ions. I think of a cluster of nonmetals that are bonding to themselves by covalent bonds, but somehow they have a charge that's bonded to something with another charge. So if I look at my choices, I have 2. Hydrogen carbonate is a polyatomic ion, and so is the ammonium. Now, if I don't know that, I can find these clusters of nonmetals, which I call table what the heck is that, because it's a cluster of something that doesn't look familiar to you, or table E. So let's go there. So here's table E in all its glory, and we have the ammonium ion, a cluster of nonmetals that have a charge, and then we have our hydrogen carbonate ion right there, another cluster of nonmetals with a negative charge. Now you may say, well, how do these have both ionic and covalent? Well, we know that nonmetals will bond with themselves by sharing electrons. They have to because they both have high attraction for electrons, which means they attract them greatly, so they're forced to share. But somehow in their formation, they either gained an electron they shouldn't have, or created a scenario where they had an extra proton. Okay? So that allows them to attract to things that are also positive or negative. Okay, let's go back to the question. So from table E, we know HCO3 is -1, which means it'll attract to a sodium +1. And right there, in between these two ions, don't forget, this cluster of nonmetals collectively is -1. So the whole thing is -1. This thing is +1. This is an ionic bond. Ionic bonds are between things that have positive and negative charges. Now, inside the polyatomic ion, you've got nonmetals. And this H would be bonding to this carbon by sharing electrons, a covalent bond. And covalent bonds, as I've already talked about, are between nonmetals. They're forced to share. So you have both. So anytime I'm asking for both an ionic and a covalent compound, I'm looking for a polyatomic ion bonded to something. So you had two choices here. You could have picked sodium hydrogen carbonate, or you could have picked ammonium chloride. Both are salts, both are ionic, but within the polyatomic ion itself, there's covalent bonds as well. So either sodium hydrocarbonate or ammonium chloride, one or the other was necessary. You don't need both. Number 72. Number 72. Explain in terms of electronegativity difference. So we have to explain in terms of electronegativity difference. That's the difference between the attraction of electrons in the bond between the atoms. Why the bond between hydrogen and oxygen in water is more polar than the bond between hydrogen and nitrogen. Okay, well, a polar bond, we're not talking about molecules. So a polar bond really describes unequal sharing. We've already talked about this in another problem. So they're picking on this test. Unequal sharing. Well, why is there more polarity in the bond between the H and O? Well, because oxygen is a little more electronegative, okay, than hydrogen as compared to nitrogen to hydrogen. So let's go to table S and look at the electronegativities of each of these atoms, which measures the attractions for them. I drew this pair a little closer to the oxygen than this pair closer to the nitrogen because oxygen is a little more electronegative, so it creates a greater unequal sharing than this one. But to confirm that, let's go to reference table S. And here it is, table S lists all kinds of information, symbols, the names, ionization, electronegativity, melting, boiling, density, atomic radius. We're going to look at electronegativity. Now hydrogen, okay, from reference table S is 2.2. So it's going to stay the same for both, right? Because we have an oxygen and an H, and then we have an oxygen, an H, should draw it this way. Let me just change it around. Just trust me on this one. Okay, we're going to do an H and oxygen, and then an H and nitrogen. Since they're both going to be H, they're both 2.2. Okay, now oxygen has an electronegativity of 3.4. Okay, so this one is 3.4. Nitrogen okay, is 3.0. So because oxygen is much more electronegative, at least by 0.4 standards, than nitrogen, that pair of electrons is going to be pulled closer to the oxygen and make an even greater negative side of this bond. This difference in electronegativity isn't as great, so this pair isn't pulled so much more closer to N. It's shared a little more equally, even though it's still unequal sharing. Both of these are polar bonds. Okay, so it's back to the problem again. So now that I wrote in the electronegativities, you can see that they want you to explain in terms of the difference. Well, there's a greater difference. 3.4 minus 2.2, okay, is going to give us, what, 1.2. It's a big difference in electronegativity. And this difference, 3.0 minus 2.2, is going to give you 0.8. Who has the larger difference in electronegativity? This bond. So it creates a more polar bond, more unequal sharing, a more negative side. So I said the electronegativity difference is greater in the HO bond than it is in the H to N bond. Okay? 73. Number 73. In the space in your answer booklet, draw a Lewis dot diagram for the reactant containing nitrogen in the equation. So let's go to the equation and let's go find the reactant. This is the reactant side. These react to make products. So we want to draw a Lewis dot diagram for the reactant containing nitrogen. So they basically want us to draw a Lewis dot diagram for NH3 ammonia. Let's do that. Now the first thing you have to realize is that ammonia is covalent. Nonmetals and nonmetals are sharing, in this case of course unequally, but they're sharing nonetheless because their electronegativities are both high. This of course is 3.0, this is 2.0 or 2.2 or something close to that, and the difference in their electronegativity is low because they're both pretty strong, so they're forced to share. So this is not going to be an ionic drawing where we have dots and brackets. Like sodium, okay, has 1 valence electron, chlorine has its 7, and if you remember, their electronegativity difference was huge. This I believe was 0.9, this is 3.2, and that's a huge difference. So large of a difference that chlorine, which by the way should have 7 of these X's or dots, okay, it takes that 1 electron and makes it have a complete octet called, which is now 8. Let me just draw that in there. And now, because it gained it, we say that everything inside is -1, and the metal lost all of its valence. Everything inside now is +1, and they stick together by an ionic bond. This is how you do metals, nonmetals, but this is nonmetal, nonmetal. So we're not going to do it this way. I'm showing you to remind you of what not to do here. You have to know if you're sharing or transferring. So N is the central atom. H's are terminal. They make 1 bond because they only need 2 electrons. I start with 5 valence electrons. Nitrogen has 1, 2, 3, 4, and 5. Now, how do I know it has 5 valence electrons? Because it's 2-5 if we go to the periodic table. So nitrogen right here is 2-5. It's in group 15. Take the 1 away. It has 5 valence. It needs 3 more electrons to fill its octet. So it needs 3 more electrons to share with. Okay, that's why it's NH3. Now I'm going to draw in the hydrogens, which donate 1 electron because they have 1 valence electron for the same reasons. And lo and behold, there is our Lewis dot diagram showing the covalent bonding, the sharing of electrons. And you notice, if I was to draw circles, you don't have to. Nitrogen now, by sharing electrons, 1 each by each hydrogen, feels like it has 8. It was 2-5, but by bonding, that central nitrogen feels like it's 2-8, which is the same as its noble gas counterpart, which is neon. So it feels like neon, a noble gas. The octet rule is satisfied. Number 74. Okay, number 74, classify each mixture using the term homogeneous or heterogeneous. Now, homogeneous means the same throughout. Hetero is different throughout. Now, heterogeneous matter can only be a mixture. All right, and mixtures can be homogeneous if there are solutions. And a solution means they completely dissolved. Okay, this means that the two components or two or more components are not dissolved. They're in a haphazard way, not bonded. Now, homogeneous matter could be bonded as compounds or elements. Well, let's see what we have here. We have two mixtures, so we're not talking about elements or compounds here. These two mixtures are what we're talking about. Mixture 1 is NaCl in water. It's colorless, which means the solid completely dissolved. No visible solid, okay? And the key here is that dissolved. It's colorless because it is dissolved, okay? So this screams solution. A solution is a dissolved homogeneous mixture. And we would write this as NaCl aqueous. And really what that is free ions are now available to move about the solution. Now, iron filings in water, okay? This observation is we have a colorless liquid with black solid on the bottom, which means it didn't dissolve. We just have a lot of water. And then we have, of course, the iron on the bottom. Total heterogeneous. They're not mixing evenly. There isn't an equal amount of iron and water throughout. So this has to be heterogeneous. Okay? One's a solution, one is not. They're both mixtures because they're not bonded, but the key here, the homogeneous means the same throughout. In solutions that are dissolved, the first drop is the same as the last. Here it's not. A lot of water and then the filings. Okay? So what we have here is mixture 1 is homogeneous. It was a solution. It really was NaCl aqueous. You don't need any of this, but it's the same throughout. And of course, mixture 2 was heterogeneous, not the same throughout, not dissolved. Number 75. Number 75, determine the volume of the iron filings produced to produce mixture 2. Well, the only information they give me about the iron is that I have its mass and its density. And we should know that density is equal to mass over volume. Now, if you did not know that, believe it or not, there is an equation on table T that shows you that. And here is table T, and table T shows you the formulas of some math calculations, or some formulas of things you'll need to do some math calculations in this test, and one of them is density. So this was a density question. Density is mass over volume. So again, if you needed that reminder, there it is in table T. So now that we know we need this formula, let's plug in. The mass is 15, okay, 0.9 grams, and the density is 7.87. All right, and what we knew is we're going to solve for the volume now. Okay, and now this becomes just a math problem. And algebraically, V is equal to 15.9 over 7.87. Now, what did I just do there? Okay, I just switched the V here, but what I did was I multiplied this side of the equation by V over 1. I multiplied this side by V over 1. Notice the V's cancel. And I multiplied this side, okay, second thing I did, I could have done at the same time, by what? 1 over 7.87, so this cancels, and this by 1 over 7.87, okay, and that's essentially what I get here, a little algebra. Now I just solve with my calculator, and what I get a value that is equal to 2.02, and the volume is going to be in centimeters cubed. Now I should have used my units here, bad Grodsky. Okay, 15.9 grams over what, grams over centimeters cubed, so the grams would cancel, and 1 over centimeters cubed is centimeters cubed, but they're not looking for the units, just this number. They didn't ask for significant figures. So we don't have to follow that rule, although we did actually. 3 significant figures, divide by 3, you get 3 significant figures. And the answer 2.02 for number 75. Number 76. Number 76, describe a procedure to physically remove the water from mixture 1. Well, mixture 1 is a solution. It's dissolved. What you cannot do is filter out, okay, particles that are dissolved. They're surrounded by water, so it's not going to work. So you cannot think filter. You cannot filter a solution and get solids out. You've got to get that out of your head. No way. What we can do is use what? Evaporation. We can boil off the water, right? And we'll leave behind the salt. We did this and recovered salt from a lab. We had hydrochloric acid, okay, and we had some sodium chloride left, and we boiled off the water. We produced sodium chloride solution, right? We had an NaCl solution, just like that, and we put it in an evaporating dish, and we heated it. The water evaporated, and we're left with the solid compounds on the bottom. So the answer is we heat till all the water evaporates. Okay, and it goes many ways to say that, but again, you cannot say filter it off. You have to say that you're boiling off the water, which is a physical change, right? We're separating a mixture. In this case, the mixture is homogeneous mixture, and we're separating it, okay, by physically boiling the water. And boiling and evaporation, freezing, all the phase changes are physical separations. Okay, number 77. All right, so we've got a laboratory activity. Here's the reaction, and here's the procedure. Here's some observations. Hey, let's not get ourselves crazy. Let's go see what they want. Number 77, state one observation, just one, that indicates copper plus 2 ions became copper atoms. Okay, well, let's go for observations. Okay, solution is blue-green. The surface of the aluminum foil appears partially black. The beaker feels warm. The liquid beaker appears colorless. The reddish-brown solid is seen at the bottom of the beaker. Well, wait a minute. This sounds very familiar. Didn't we take aluminum foil in a lab, drop it in a blue copper chloride solution, and we get a reddish-brown solid and a clear liquid that we filtered away? Yeah, it's crazy how these reactions look eerily similar to our labs. Any case, so the observation that we need that indicates that we made pure solid copper atoms is that we had a solution that became reddish brown. Okay, aluminum foil has got that silvery kind of luster to it, and we got that reddish brown solid appeared. Even if you forgot it was reddish brown, look at the observation. Oops, don't do that. Guess they'll go crazy. We're making a solid is appearing, even if you forgot they're reddish brown. The only solid, okay, that should be appearing that's new, of course, is the copper, because this is a, guess what? A chemical reaction. All right, so a reddish brown solid is seen, number 77. So there, a reddish brown solid is formed, a solid is formed, and it has to be copper. Also, you probably could have mentioned something that the solution went from that blue-green to colorless, meaning the copper came out of solution. But either way, this is a good answer here. You made a solid, or the solution went from blue to colorless, like the lab. Okay, so number 78. So if you wanted to use something other than a reddish-brown solid for number 77, you can see in the procedure, you start with a beaker, completely dissolved copper chloride, and it's blue-green. Okay, after you observe the beaker after 10 minutes, the solution is colorless, which means all the copper came out of solution. So that's something else you could have used as well. All right, number 78. Describe one change in the procedure that would cause the reaction to occur faster rate. Here is our question. As you probably were waiting, we haven't seen a rate of reaction question yet, okay? So what's one change in the procedure that would cause the reaction to occur at a faster rate? Well, my friends in chemistry, you probably could list any factor that affects effective collisions, and that probably could be temperature, okay, I guess I could accept other things as well. If you had to say catalyst, I guess I could have to take it, but temperature is probably the best one. Probably increasing the concentration of one of the reactants, right? That's increasing concentration is a factor, temperature is a factor, maybe increasing the surface area of the aluminum, right? If the aluminum solid is going to expose more of its atoms if it had a higher surface area. So you could have a higher concentration of this solution, right? If it was a 1 molar, if you had 2 molars, then you would have more available atoms to collide with the aluminum if the aluminum had a higher surface area and a higher temperature. Those to me are the greatest answers. I mean, I guess I could accept a catalyst, okay, and I could not accept a pressure because there's no gases here, right? Solids and liquids aren't affected as much as gases are. So as I've been writing here, increase the temperature or increase the concentration of copper chloride. I thought I paused it. Hello. All right. And I could have also put increase in the surface area. Number 79. Number 79, state one safety procedure, just one, that the student should be performed after completing the laboratory activity. Again, this is a common sense question. You could probably make up anything as long as it has something to do with being safe in the laboratory that makes some sort of sense. So this has to be after, okay, completing a laboratory procedure. So wearing goggles I can't accept. So you have to read carefully. Okay, cleaning the equipment, putting it away, disposing of any chemicals, those kind of things. Number 79. So I said wash lab equipment, put away, wash hands, okay. Many different things you could say here, as long as it has something safety related, but you had to pay attention. It's after the reaction is done. Okay, number 80. Number 80, we have a little blurb here. Let's just go to the question. State in terms of pH scale. So you've got to answer the question in terms of the pH scale. 7 is neutral, above 7 is basic, below 7 is acidic. Why this beverage is classified as an acidic? Well, what's the beverage? It's a carbonated beverage. CO2 is forced into a beverage. Okay? When it's open, the beverage has a pH of 3. So 3 is below 7, so it's in the acidic range. It's just that simple. Number 80, let's go to the answer booklet. So I said a pH of 3 for the soda or the carbonated beverage is below a neutral pH of 7. I mean, you could say this so many different ways. Okay, the beverage is acidic because its pH value is below 7. A pH of 3 is in the acidic range in the pH scale, but you had to include the pH scale somehow in your answer. Number 81. Using table M, identify one indicator that is yellow in a solution that has the same pH value as this beverage. Okay, so we're going to go to table M, and we want an indicator from table N that is yellow, okay, at a pH of 3. That's what they're getting at here. They want you to go to table N, which is a table of indicators, and find me that goes yellow, okay, at a pH of 3. That's what they're trying to say here. So table M, here we come. So our task here at table N is to find a yellow color for an indicator at a pH of 3. Methyl orange, okay, to read these as a review, anything 3.1 or lower is going to be yellow. Anything, okay, 4.4 or higher is going to be yellow. I'm sorry, anything 3.1 and lower is red. I'm not looking at red but say yellow. And anything 4.4 and higher is yellow. So I'm not sure methyl orange is the best candidate because it's in the middle here. it's going to be, well, less than 3.1, so it's going to be in the red range. Okay, Bromothermal blue is yellow when it's 6.0 or lower. So I like that one. That screams to me. Phenolphthalein is colorless, 8 and lower. Since 3 is less than 8, it's not going to work. Litmus is going to be red, 4.5 or lower. Brome Cressyl green is going to be yellow, 3.8 and lower, but my value is, of course, lower than that at 3, so that's another winner right there. Okay, so I've got bromothiamyl blue or Brome Cressyl green, and thymol blue is going to be yellow at a 3 a yellow. So I've got 3 winners I can pick from. I'll pick thymol blue. Okay, but again, reading these, okay, you can clearly see that the Brome Cressyl green, okay, the thymol blue, and the bromothiamyl blue will all be yellow at a pH of 3. So I picked thymol blue, but you certainly could have done Brome Cressyl green and bromothiamyl blue, but I picked the one that was easier to spell. Okay, you know that. Number 82. After the beverage bottle is left open for several hours, this is the carbonated beverage question, the hydronium ion concentration, hydronium ion is H3O plus. Yeah, that's water holding on to a proton. That's from the acidic, okay, or the acids, okay. In the beverage, decreases. Wow, 1 over 1,000, which means decreases 1,000 times. So if our acid solution is decreasing 1,000 times, it's getting more basic, right? Now you say, Mr. Grotsky, how do you know it's hydronium ion? Well, my friends, in chemistry, we have something called polyatomic ions. Let's review. Table E is your friend here. And there it is, the hydronium ion. For those that can't see, open your eyes. And there it is, the hydronium ion in table E. So that is responsible for the acid range. Water holds on to protons. It accepts a proton based on the other definition. Okay, Bronson-Lowry for those that want to be in the know. Okay, so they're talking about the acid quality of the solution is decreasing. Well, that means it's getting more basic, as I've said. Now, the pH is originally at 3. And if it's getting more basic, the pH is going to increase to some value. Now, how much? Well, I know the acidity is decreasing 1,000 times, so the basicity is increasing 1,000 times. And we should know that the pH scale is based on logarithms, okay? Base 10 logarithms, right? A log of 1, okay, is really 10 to the 1, which is 10. Log of 2 is 10 to the 2, which is, guess what, 2 zeros, 100. And a 10 to the 3 is equal to 1,000. So this 1,000 times represents this exponent 3. pH scale takes the exponent of the concentration. Any case, we know that this is going to go up, okay, 1,000 times is equal to 10 to the 3 from your math class. 3 zeros. Well, if you remember, pH is the positive value of the H plus ion concentration. So pH comes from the exponents. So really, this is going to increase 3 times. And it's going to go to the pH of 6. Remember, every pH integer is really a 10. So if you go up 2 integers, it's really what? 10 to the 2, 100 times. 10 to the 1 is just 10 times. So because I'm saying the basicity is increasing 1,000 times, okay, that means 10 to the 3, okay, and the 3 is what we use because pHs are based on this exponent. Case in point, if the H plus ion concentration or the hydronium ion concentration is 1 times 10 to the negative 6 Guess what? We say the pH is equal to 6, right? We took the positive value of this exponent. Now, let's go back to the pH of 3. When the pH was equal to 3, the H plus ion concentration was equal to 1 times 10 to the negative 3. And if this number is going to go down 1,000 times, it becomes this number. Isn't 1 times 10 to the negative 6 for the H plus ion, or H3O plus, 1,000 times smaller, right? So the pH increases 3 integers because you're changing your exponent. Okay, and each exponent is a 0. So the pH is a 6. Okay, let's go to the table or booklet. So our pH is 6, number 82. Number 83. All right, so we got a little blurb here. I'm going to go right to the question. State one beneficial use of polonium-210. I have no clue, so I've got to go back into the reading. Polonium-210 occurs naturally but is scarce. It's primarily used in devices designated to eliminate static electricity. Wow, right from the reading. So 83 eliminates static electricity. So I said eliminates static electricity. Okay, I guess in machinery, I should say. Okay, it also removes dust from camera lenses. It's also in the reading. Okay, so those are the two examples. This is a reading comp question. Nice. Okay, so number 84 is next. 84 says complete the nuclear equation in your answer booklet for the decay of polonium-210 by noting the notation of the missing product. Now, if I go into my reading, because I don't know if polonium-210 is in table N, but they say in the reading you can be created by bombarding bismuth with neutrons to create bismuth-210. The bismuth-210 undergoes beta decay to produce polonium. Okay, polonium-210 has a half-life of 138 days and undergoes alpha decay. We needed that, okay? So polonium-210 undergoes alpha decay. So let's go to the answer booklet, number 84. Well, I thought we would need it, but they gave us the alpha particle there. And if we didn't have that there, we can go to table O and read that directly. Okay? So, how do we do this? And so many students get this wrong. If you did, please pay attention, because this is an easy question. Put an equal sign above, and we'll do this in a different color. Yeah, let's go like green. Okay? Equal sign. How about we don't go do it in green because it doesn't come out very well. Let's try this again. So, put the equal sign on top. 210 equals 4 plus what? Well, 4 plus 206, right? 206 plus 4 is 210. Use your calculator. No shame here. Okay? 84 on the bottom numbers has to equal all the bottom numbers on this side. 2 plus what is 84? Okay? And that would be 82. Right? 82 plus 4 plus 2 is 84. 206 plus 4, right, if you have to, equals 210. All the numbers on the top on one side have to equal all the numbers on the top of the other. And then you have to go find that element 82. Let's go to the periodic table. Atomic number 82 is lead. You could have looked up 82 in table S as well. And you remembered everything loves to decay back into lead. So everything 83 protons and beyond has unstable nuclei. Okay, all these isotopes beyond are not stable, so everything decays back into lead. So this would be Pb, and you certainly could write this bigger. Pb 206 82. You could also say lead. Oops. You can also say lead dash 206, but you have to make sure you say that isotope. But again, these numbers I generated from equaling the numbers on top and the bottom. Don't get this one wrong. Number 85, the last one. Yippee! Number 85, determine the total mass of an original 28 milligram sample of polonium-210 that remains unchanged after 414 days. So this is going to be a half-life problem. And I start with a 0 line. 0 half-lives. I'm going to use this line. I'm going to, conserve. And I have an original sample of 28.0 milligrams, and I have 0 time. And they said it remains unchanged after 14 days, and they want to know how much mass, okay, is remaining after 14 days. So the total time here is 14 days. That's great, but I need to know how many halvings have occurred. In the reading, I remember looking through that, they actually gave me a half-life of 138 days. That's pretty darn important. Okay, so if I know that each halving, okay, is 138 days, then what I'm going to do is take the total time and divide by 138 days. And when I divide by that, put that in my calculator, this equals 3. There are 3 of these half-lives in these days. So 3 halvings have occurred. If each half-life is 138, which is the amount of time for it to halve, and I have this total time of 414, I divide by that and I get 3 halvings. Okay, so we have the first halving. Well, cut 28 in half, I believe that's 14. Second halving, cut it in half again, that's 7. And the third halving, cut 7 and a half, and this is 3.5. So the answer is 3.5 grams will remain after 414 days because that's really 3 half-lives. Answer is 3.5 grams. Of course, the answer is 3.5 milligrams, and I forgot that unit there, but no harm or foul because they put the unit in there for me. Okay? So I hope you enjoyed. I certainly did. Look forward to the next one. I am. Okay? Any case, hope this helped. Okay? Take care.